Here I have an interactive website where you can solve a one-dimensional Schrodinger equation numerically using the Numerically method. Here I can define a potential energy function, and I choose a unit such that h bar and the mass of the particle is 1. You can choose other unit and update the values. Here is the potential energy function plotted, but you can actually use your mouse to drag along the plot to change the shape of the potential energy function. Now, if we want to solve the Schrodinger equation for this arbitrary function numerically, this is a second order differential equation. What we need is a potential energy defined at every point in x, which we already did. We also need an energy value. So you need to provide this energy value first. For now, when we solve this equation, you can plug any numbers. Discretization will come later, which we will see in a moment. For now, you can plug in any arbitrary number. We also need two initial conditions because this is second order differential equation. We need two initial conditions, so we can provide for a point in x, we can provide the value and the slope for psi. You can provide that number by dragging on the second canvas. So we provide a value and a slope. And then we provide an arbitrary energy. Now, this is a solution for the Schrodinger equation. However, in order for this function to be meaningful, that is, it must represent a physical particle, it needs to be normalizable, which means that if you integrate the square of this function, you will find that the area below it is infinity. So that's not good. Physically, we expect that on both ends, because when the potential goes high, the probability density for the particle should vanish. Therefore, we expect that the solution at both ends should vanish. This solution goes to infinity at both ends. We can do that by first specifying an initial condition at the left end by providing a very small value so that the boundary condition is satisfied at the left end of the plot. It vanishes at the left end. Now if we plug in any arbitrary energy, you can see that it doesn't necessarily vanish on the right end. But if we scroll this energy bar, you can see at certain energy values between these 2 points, it does vanishes. It flattens, so between these 2 points, this wave function would vanish. This is where the discretization of the energy levels comes from, mathematically, numerically. So there you find between these two energy values, there's a solution where you can find a function that satisfies the Schrodinger equation and also satisfy the boundary condition on both ends, which gives a normalizable wave function. You can keep scrolling to find the excited states, and you can automate this process using the binary search algorithm. And you can see we find the first excited state, the ground state first, and second excited states.